Hello everyone, welcome to my second and last lecture. And I will not be around tomorrow and the following days, unfortunately, because tomorrow I have a meeting to attend in SSB in Koç University. And after that, I have to go to Ankara to attend the Photonic workshop there. And I have a talk also to deliver there. And that's the reason this is the last day of my attendance here. And my title today will be something different, nonlinear effects in photonic integrated circuits, but we will be mainly talking about waveguides again. And when I say waveguide, it's always actually a piece of fiber or an integrated waveguide, basically the underlying physics is the same, so you can actually consider them as interchangeable. And the content will be actually what is nonlinear optics, and then I need to introduce nonlinear polarization, and also we will need to talk about a little bit about the crystals or non-crystal shape, and then we will talk about the nonlinear dynamics. And today we will have some coding session. I prepared some codes. I upload them onto GitHub, which you can always access. It's publicly available now. And I will also explain the code when we have the time. And then at the end, I will talk about why we need nonlinearities in optical computing, because why we are actually struggling with it. The first of all, we will need to talk about the dielectric media. Of course, we are playing with glass or the glass-shaped materials, and yeah, we need to consider them as. Let's see. Ooh, my text has. Oh. Give me a second. Unfortunately, I don't have a Windows machine with me, and let's give it a shot. Okay, we are dealing with dielectric media, and we have an electric field. We are letting it propagate inside. As you can see, this is actually a piece of waveguide. And what happens when we send an electric field to this medium? Well, we will have this induced polarization density, and polarization changes. And because of that, we will have nonlinear dynamics. And this is actually the background slide from my electromagnetics and also the basic optic course. And in a medium where we consider this homogeneous, non-dispersive, isotropic, and linear, everything is, really nice. You have to derive a wave equation by, taking the curl of this expression, and then you will get a nice wave equation by assuming a homogeneous isotropic medium. And this is nice, right? You have an E field, and because of that, you have the polarization stuff, and everything is nice. But unfortunately, in real life, the materials are acting nonlinearly. Nonlinear means that when you send one, if you get two, when you send two, you will not get four. And it will be a difference, right? And now, when in real life, unfortunately, the relation between this E field and the P is actually not linear. And because of that, depending on the medium, you will see this nonlinear polarization, and because of the nonlinear polarization, you will get frequency shifts. My background is lasers. Around, let's say, 12 years ago, I joined a laser group. It was fiber laser group, and since that time, I'm dealing with fibers. And I noticed that lasers are actually limited in terms of their colors. And let's say I'm a fiber laser guy. If you build a fiber laser, the common laser types you will build is ytterbium, 1 micron, it operates on 1 micron, aluminium, 1.5, thulium, 1.7-ish, it's actually below you can do it, and holmium, 2 micron, which is 2.1. But they don't cover all the spectrum. So what you need to do, you need to play with nonlinearities to convert frequencies. That's the reason the nonlinear optics is actually by itself the giant topic to investigate. And also in quantum optics, I'm sure you should already mention, you need this nonlinear convergence to generate entangled photons, right? And also you need nonlinear crystals to squeeze light. So squeezed state, entangled state, they need nonlinear crystals. So what's a coherent state? Laser. So you need laser and nonlinear crystals to do quantum optics. And what you see here is actually what we call second harmonic generation. You send 2 photons and then 2 photons somehow combine and generate one photon after passing a crystal. And what you see is actually from an infrared light, which is invisible to our eyes, inside of a piece of fiber, it generates a full spectrum of the visible colors. So it's actually sharp continuum generation. Normally it's actually white light, coherent light. And by heating the igniting, it's dispersed over the space in terms of wavelength. And because of this nonlinear response of the media, you have to modify the wave equation. You have to implement this nonlinear polarization response. Okay? And when you put it there, you will notice that actually we can always explain this polarization as in a better term. It looks like a Taylor expansion, right? What we have actually is the psi, this tensor of the material, let's say, property, and it tells us a lot of interesting stuff. Depending on the property of the material, the orientation of the material, you will be dealing with chi2, or chi3. And if you are really wondering about, for those layer souls, I recommend to read or study, it's better to study Robert Boyd's Nonlinear Optics book, but we will not cover what's going on there, but I can easily say that it is a giant tensor with complex values. It's really funny. And as I mentioned, depending on the material, this chi2 and chi3 changes. And because of that, what kind of nonlinear phenomena you will observe in the medium will change. For instance, what else I can say? I can easily say that second-order susceptibility is actually for crystals. Okay, the crystals have nice feature in the molecular orientation. What was the definition? Second-order susceptibility is non-zero only for the media that may have inversion symmetry of the molecular level. Inversion symmetry is one of the molecular orientation term, and if you should think it like if you have inversion symmetry in the molecule, the medium is actually identical to its mirror image, and because of that, they have this. They have this type 2 is actually in crystals, and we use nonlinear crystals to generate second harmonic generation, or most of the time wave mixing, etc. But when you deal with wavelengths, our original concern is actually our original concern is actually the silicon or silicon nitride materials, like they have actually different type of molecular symmetry, and because of that, they don't have chi2, they have chi3, and because of that, they have different nonlinear dynamics most of them. But of course, this is an idealization. We can always get second harmonic generation in other types of materials as well, in these materials which I mentioned. And just for fun, let me mention about this the famous second harmonic generation thing. You have a laser, you send this laser light to the crystal, and because of this crystal structure, as I mentioned, 2 photons combine, and they, because energy should be conserved, you will get another photon with the highest energy, and that's the reason what happens is actually, in terms of wavelength, the wavelength is divided, okay? We had red, now we have pinkish or bluish, so blue actually. And it's really common, it's everywhere. You don't have a green laser, it's a red laser, but every green laser you use has actually nonlinear crystal in it. I mean, because they have lasers medium around young or something like this, and these neodymium yak. These yaks, actually, this neodymium auditorium works in 1 micron, around 1064. And after the nice cheap crystal lasers, they have a nonlinear crystal inside, and they convert the frequency. And that's the reason you see green, but you cannot see temperature, sorry. And most of the crystals, it depends on what kind of a wavelength you want to use, what kind of length you need, and you can always get this, most common ones, BBO, KTP, or regional. Most of the time we deal with BBO or KTP. Regional, I haven't used, but I know that it's an interesting material. But, as I said, we are not in crystal business, we are in different materials. Our common materials are silicon, and silicon nitride, and they don't have this crystal structural orientation. That's the reason they have this country non-linearities. And let me tell you how nonlinear, or when you compare with each other, how nonlinear are they, and which reflective indexes and transmission transparency windows they work. And as you can see, they don't have Chi2, they only have Chi3. We have CPAP, right? And this guy, and its nonlinearity is actually around, just deal with the order of magnitudes, okay? From silicon to silicon, what happens? 10 times, right? No, 10, 100 times. From silicon to silicon nitride, 10 times. And the reflective indices are actually very different. The transparency windows for silica is actually silicon nitride, not bad, right? We are going to deal with this material and we want to do nonlinear optics, so the nonlinearity coefficient, nonlinearity index is actually important for us. It tells us for, let's say, same amount of laser light, how much nonlinear dynamics, or what's the state of the nonlinear behavior, how it will change, okay? And based on that, you can actually direct your medium, what kind of a media I want to study. And silica is here because it's fine. For us, it's a piece of fine. And you can have silicon alongside, right? And also silicon nitride, my favorite. We are actually working on silicon nitride in a couple of slides. I will explain why we are working on silicon nitride rather than silica, right? So it's silicon. Because as you can see, silicon has a very better nonlinearity when you compare with silicon nitride, but somehow it ends up here, not here. Yeah, that's it. And in addition to that, because of the Chi3 nonlinearity, the fundamental nonlinear dynamic you will see is this curl effect. Okay? The curl effect is really funny. It tells you that the material has a nonlinear. So the material has an index, right? The reflective index volume. Curl effect tells you that you can change it by shining light into it. It's a really small change, but you can change the reflective index of the material by just shining light on top of it. Okay? While the light there, it actually creates a response, and because of that, the reflective index changes. How it changes? It changes according to the intensity. Intensity is nothing but absolute square of the field. Okay? So, as you can see, there is something related to the absolute square of the field. Is this equation linear? No. This is nonlinear, right? Because of that, we call it nonlinear optics. Unfortunately, it's a bonus, but this is the only explanation we have in nonlinear optics. Okay? When I studied in this laser group, and everybody's talking about nonlinear optics, and I was explaining some big stuff, but when I see nothing but an absolute square, I was like, nah, So, because of that, what happens when you shine a light to a piece of glass? Because of this light, the reflective index changes. And later, because of this change, which we created, we get affected by it. Okay? The light we send first will change the reflective index, and because of that, it will get affected and it will generate infinite uses. Okay? This is the essence of the curl nonlinear. This is the essence of actually nonlinear optics in these materials. Of course, how to select the medium, this is important, right? We can always check the nonlinear reflective index, which we did, and silicon was better than silica or silicon nitride, right? We also check the transparency window, which is okay, but we should consider other effects as well. For instance, absorption or other types of losses. Let me tell you this. Again, silicon example. when you compare it in terms of this third order nonlinearity and stuff, can effect is more than 100 times large. Raman gain, which we will talk about that in the following slides, is again more than 1,000 times large when you compare silicon, this is silicon to silica. Okay, this is a piece of fiber, this is the waveguide you can generate immediately and cleanly. So this is nice, right? We should be all working here. Or we should just compare with silicon nitride, but we need one of those. Again, silicon nitride will be less nonlinear than this guy. But in reality, silicon has a weird behavior. It's called two-photon aversion. Two photon converge and absorbed by the medium, and it goes to heat. Yes.
You said a slide before that the electromagnetic distance, the products to the material, it affects material and consequently it affects light that we stand on.
Yes.
Right? Is the effect instantaneous or does it take any time?
There's a tiny delay, around femtosecond range. Do you guys know how is femtosecond? Which range we are talking about? You should know this. That's mathematics basic. Any unit here, 0, okay? 10 to the 0. 10 to the minus 3, milli. 10 to the 6, minus 6, micro. Thank you. 10 to the minus 9, nano. The correct answers are fading here. Nano. 10 to the minus 12, pico. Thank you. 10 to the minus 15, femto. This is the range and all families. Nano is giant for you. But femto is not shortest. 10 to the minus 18, octo. Thank you. Octo. So, it's a response in terms of femtoseconds. At best, slows picosecond. Okay? So, as you can see, we have two photon absorption in silica. That's the reason we don't recommend to use for nonlinear optics, because when you pump light, rather than this new frequency generation occurs, it gets absorbed, it creates heat, and if you don't cool it well, what will happen? You will damage the material, so you will have a burned chip, which you spend a lot of time, a lot of effort, and the precious time, right? Because you need to graduate. And that's the reason, rather than using silicon waveguides in torch, we are dealing with silicon nitride, because silicon nitride, in terms of two-photon absorption, is really way better than silicon. What else? Yes, we need to talk about wavelengths, right? So in wavelength, what happens? Yesterday's lecture, you send light and it propagates, right? We need to now consider the propagation of light under nonlinear conditions. What you need to do is, as I mentioned, you just need to split the polarization in terms of linear and nonlinear terms. You just need to modify your wave equation, and then you can play with it. What you can do, let's say, the simplest case is actually the waveguide with single mode, single spatial mode. It means that nothing changes in space. You have just one nice light shape which will fit inside the waveguide, and no matter what you do, nothing will happen to that. Okay? You can bend the fiber, you can bend the waveguide for the silicon structure. There will be losses, but spatial change will not occur because it's just single mode, right? So it means that there's no spatial change. So the easiest case is this, right? What will happen then? You need to consider only the temporal change, not the spatial change, because there's nothing to change. So you can write the E field in terms of an expansion, and you can have this spatial distribution. You can have this small variant pulse envelope A, which we will be using in a couple of minutes, and you need to also consider the propagation constant, and it will come and define also the wavelength dispersion, and it's actually nothing but the Taylor expansion according to the refractive index of the medium. Okay? The refractive index is wavelength dependent, and you need to multiply it with the wavelength and divide it by the speed of light in vacuum. And when you open the Taylor expansion, you get this nice propagation constant and also the second order dispersion, third order dispersion, and you will see it causes to light to spat in terms of the speed, because different wavelength have different speed, and how much it will spat, you can get the value from there. And if you do that, and assume, as I said, assume just single mode, no special changes. You can always drop this guy, and then you can write a wave equation like this. What we have, A is our solid complex envelope, which we are studying now. It depends on Z and time. Z depends because it propagates in Z. So in time, it has a signal, it's a signal in time, but it changes with Z, which is the propagation happening inside our waveguide. And this is this, definition. We have this beta 1, which we will in a minute we will get rid of it. We have beta 2, this second order dispersion. This is the dispersion which I tell you because of the different colors, there will be different speeds, and because of that, your signal will spread, disperse. In time, we have this, it's the combination of gain and loss. Depending on that, you can consider whatever you want. And this is the term. This is the great guy you need to study. What's this? Intensity. Right? That's what's coming. So this is actually a coefficient according to the waveguide we are working. So this is coefficient, this is complex volume, this is intensity, this is nonlinear. Okay? So this is actually a form of nonlinear equation. It's written in 1 plus 1 dimension. Okay? 1 dimension signal propagates in the plus dimension. And I don't like derivatives. You will see at the end of today. I hate derivatives. I like to get rid of them always. So we need to get rid of this guy. It's actually time. We are observing everything from outside. Okay? I don't need to take the derivative. I don't like it. So I can get rid of it by making a change of reference point. Rather than observing everything from outside, I can start to observe everything on top of the field I am propagating. Okay?
Why do they call it Schrödinger equation? Because it's all classical now.
Exactly. It looks like nonlinear. It looks like Schrödinger equation. There's no relation with Schrödinger, the quantum part of the Schrödinger himself. It looks like that's the similarity, because of the similarity, they name it like that in the theoretical physics. It's really funny, it always confuses people, it sticks there and it's always like. And now, by doing this transformation, by just considering the time, which is kind of retarded. We call it retarded time, funny name. And by doing that, you can get rid of loops. You can get rid of the first, and this is the first derivative, you don't need it. And this is the final equation you should consider to study nonlinear dynamics happening to any light inside a single mode waveguide. That's it. There's no special term because it's single mode. What happens is in time and frequency, right? Time and frequency is linked with each other thanks to correct answer. We had some additional point. Thank you. And this is the nonlinearity coefficient. And as you can see, it's defined by the nonlinear index of the medium, and also the central frequency of the medium, the central angular frequency of light. And we have the speed of light. Area affected is the area which light propagates. Okay? In a way that this actually scales with the medium you are propagating. As I mentioned, single mode. Let's talk about single and multi-mode. Very topic fibers, and basically it's the same. You have this piece of cable, and it only supports just one shape. If you have this shape, it will couple into the waveguide, it will propagate as much as you want. It can go kilometers thanks to the low loss fibers we have. Okay? And what happens, as I mentioned, everything changes in time. There's no change in space. That's the reason you need to consider this nice nonlinear Schrödinger equation. Dispersion, what happens to your time signal, and nonlinearity, it will create whether frequencies or not. It's simple, your life is simple, it always gets the beat standard of optics. According to optics, the beautiful thing is Gaussian, right? If you have a Gaussian beam, you have the perfect laser. So if it reverses, it only has temporal evolution, and it has lots of applications, fiber lasers, fiber optics, long distance communication. But if you get the core slightly larger, everything's same. Material is same. The effective indexes are same. Everything is same. Just physical dimension of the core is a bit larger. It starts to accept different shapes of light as well. And now you need to consider what happens to spatial distribution of the light as well. Then your nonlinear Schrödinger equation will be a bit weird. We have diffraction, what happens to space, dispersion is still there. We have the reflected index profile, and we have the nonlinearity. In other parts of physics, people also have something similar to this. It's actually the potential, okay? And they take the derivative in time, not z, and they call it Gauss-Dennison equation, or Bose-Einstein theorem. Okay? Same thing. You just need to take the derivative in different stuff. They have parabolic index. I have parabolic index. As you can see. So this is we call spatial temporal nonlinear Schrödinger equation. Okay? And what happens is actually this is by the way an experimental result from me. We had the world's fastest camera at Caltech, and we could see we could sample ultra-short pulses in space and time. So it's actually the envelope of my laser pulse, how it looks like in real life. Okay? So as you can see, for different time, it has a different shape. Likewise, we can talk about the photonic integrated surface. Our example is the waveguide. For instance, I calculate since morning I was studying in the back to generate these simulations, and I calculated the modes of the tiny slab waveguide. We have silicon nitride here. The reflected index of the cloud is TÜBİTAK 1.47. The core is silicon nitride. This is actually the cross section from here to here. Okay? As you can see, this reflective index jumps, and light actually gets trapped here, and total internal reflection, it guides the light. And the dimension of my slab is actually nothing but 200 to 600 nanometers. It's actually really small, and I'm working on 1030 nanometers, which is the lasers of, I'm using the laser from ytterbium fiber lasers. And as you can see, my waveguide supports this shape, but for the other guy, it starts to leak. For the third guy, it's only in the cloud. It's not my core. I don't need to care about it. And after a couple of millimeters of propagation, it will dissipate and it will leak, and I don't need to care about it. This is a single mode waveguide in photonic crystals. By just thinking, just check the dimensions. Now I have a larger area, and that's the reason I can fit different shapes. Okay? And now I need to consider what happens in time and space at the same time. I like this term, spatial temporal. I have this term in both of my theses, in master's and PhD, spatial temporal nonlinear dynamics. And let's talk about what happens in this equation depending on what kind of a laser light we have, okay, and what happens to our pulse. For instance, I have a laser pulse. This is coming from my own laser. It's actually femtosecond. Now everybody knows it, right? 10 to the minus 15. 50 femtosecond, not bad, not shortest pulse, but not bad. I have 1 watt peak power. The peak of my laser is 1 watt, okay? And I'm letting it propagate 30 centimeters of single mode fiber. And what you see here is, from here to here is 30 centimeters. What happens to my one-dimensional signal? Because why I'm saying one-dimensional? I'm working in single mode. Nothing changes in space, right? I just need to consider time. And it's flooded. So this is spectrum. This is time. Okay? And what happens to it? You can see from this figure. As you can see, in spectrum, there's no big change. In time, it starts to spread. In the beginning, it looks like this blue. It looks like this blue, nice Gaussian pulse. And at the end of the fiber, 30 centimeters of waveguide, I have this signal in the intensity. It looks like the intensity dropped. But actually, there's no loss in the simulation. If you take the integral, which is the area under this curve, it will be same. So what happened? It will disperse in time. Okay? And this is a linear behavior, although the equation is actually derivative, how much it dispersed, you can take a note of it and you can double the fiber and it will be double when you double the fiber, okay? It's actually a linear relation here. Although we have nonlinearity term in the simulation, the peak power is not enough to exert nonlinear propagation. That's the reason we have a linear dominant propagation here, okay? And in spectrum, nothing changes. Because spectrum oftentimes gets manipulated by the nonlinear. This time, same situation. What changed? Peak power was 1 watt, 10 kilowatt. It's not a hard thing. You can get 10 kilowatt lasers immediately. It's cheating, you know? It's an easy to do. And we let it propagate. What happens? Again, our pulse is dispersed. There's no way of getting it because there's dispersion. But our spectrum starts to get broadened. Okay? As you can see, our spectrum gets to broaden until a certain point, and later that the pulse is actually broadened as well and the peak power dropped. So nonlinearity is not enhanced anymore. Okay? This time 30 kilowatt. Spectrum is very broader. Actually, from here to here, I'm changing the grid because it doesn't fit. Okay? Previously, it was around 1000 nanometers to 1100. Now it's around 900 to additional 100 nanometers. Okay? And from 30 kilowatts, this one. Okay. So 30 kilowatts, we go to 300 kilowatts. Our pulse is dispersed. Well, our spectrum is also broadened, as you can see. We generated new colors. We reached to around 200 nanometers here and around 150 here. Okay? This is the effect of nonlinear propagation inside a piece of waveguide.
So is this bottom figure the second harmonic or the
No, same thing. This is what we call self-phase modulation. As I said in the child nonlinearity, the light affected the refractive index and starts to get affected by it. And because of that, it starts to generate new frequencies around the central colors. Okay? This is systematic frequency generation technique.
It's more than the first one, and the minus 26.
Pardon me?
What is the order of the second one?
In terms of intensity, this is the peak power, but in terms of energy, it's same.
The value of intensity is in the order of 10 to the minus 1.
Yes.
But there is more than 2.
Yes, that's true. The number of the photons at that color is less. It's okay. But I mean, in terms of these guys also contribute. Let's say we are trying to go to here. In this case, let's say in the case of 30 kilowatts, there's no this color, right? Now we have colors. We need this way. Yeah, we are trying to reach the certain colors.
Okay, I'm not familiar with this experimental stuff, but
It's actually numerics. This is simulation. In a couple of minutes, you will get the code. Okay. What kind of other nonlinear dynamics can occur? It's actually a different thing. You can send two pulses at the same time to the same wavelength, and they start to affect each other. Let's say I have a pulse A1, which is high peak power. It will definitely get into the nonlinear propagation. And I have a really weak, low-powered light. I somehow set them at the same time inside the same wavelength. Let me tell you funny thing. They will propagate in a coupled form, and because of this high-powered A1, A2 will exhibit nonlinear changes as well, because the refractive index changed already by the other guy. Okay? And we need to solve a coupled equation, and we call this cross-phase modulation. It affects the phase at the cross. Okay? And based on that, if you have the correct terms, you can generate solitons. What kind of solitons we have is actually soliton is a stationary pulse, okay? And we can easily generate it in optics, in lasers, for instance. If you have a dispersion beta 2 smaller than 0, nonlinearity is already positive, okay? This is negative, this is positive. They will act as opposite, and they will cancel each other. And whatever you send to the piece of fire, it will glow. Okay? And it will not change at all. And we call it solid. Historically speaking, because it's a solitary solution of the wave equation. And as you can see, nothing changes, nothing changes, even though you have 5 kilowatt peak power. Based on that, actually, you calculate a soliton number. And this is soliton number. How you calculate it? You define a dispersion length, you define a nonlinear length. Dispersion length is actually nothing but your input pulse width square divided by the second order dispersion absolute volume. And also the nonlinear length is actually 1 over gamma is the material's nonlinearity times your peak powers. By just dividing these guys to each other, you get a value n, okay? And n is the soliton. If n is 1, you see this. If n is 2, you see this. It's a bit different, right? It starts to bleed. Solitons bleed, okay? And this is the reason of, this is the funny part of nonlinear optics. And these got based on solitons and such. We have Raman scattering that can also go with it. In Raman scattering, we have this is actually inelastic scattering of photons with the material. It's actually invented by, discovered by Chandrasekhara Venkata Raman, one of my favorite scientists. And what happens is when you shine light to any method, because of the method, the frequency of the light will change. Okay? And this frequency shift is actually material dependent. So in a way, you can use it to perform spectroscopy. Let's say you have a liquid, you don't know what's inside. You can shine light, you know the frequency of your medium, and you can check where is the scattered piece, and because of that, you can identify inside the liquid it should be this and that. Okay? And you can get this nice sort of frequency generation. Also, you can get Raman lasers and Raman amplifiers, one of my favorite laser types. And Raman in silica looks like this. This is the Raman spectrum, Raman gain spectrum, and there's actually a second graph here. Second graph tells you that this, like all the nonlinear effects, Raman scattering is also polarization dependent. If you send a linearly polarized light with a nice orientation with the material, you can get this high Raman peak, Raman gain. But if you go into opposite direction, you messed up and your Raman will be less. And what happens is because of the silica glass, you will have as the peak 13.2 terahertz. But in your central wavelength, you need to convert to the frequency and you need to add or subtract 13.2 terahertz. And depending on that, you will get the first Raman peak. Okay? And as you can see, from 1030, first Raman peak is around 1080. Okay? This is Raman scaling.
Is this also a simulation?
This is also simulation as well. You have to add the Raman term into the simulation. Thank you for that. So simulation time. How you can study this? Nonlinear equation, linear equation in the simplest form is this. In the most general form, it looks like this. And keep in mind that the dispersion is Teğin expansion. You can go according to as much as you want. You can go to 12th order as well. In some cases, you should, by the way, to get real simulated experimental type simulations. So this is gain and loss. This is second order, third order, nonlinear coefficient, and our CAD stuff here. This part is the Raman part, okay? And also we have something called self-stepping, as we have a derivative here, okay? And we need to solve this equation. Even this is hard to solve.
The only thing similar with Schrödinger equation is I.
Yes.
Other than that, it's all different, you know?
You completely right.
I mean, Schrödinger equation, first order time derivative, you have second order position derivative, you have first order position. So it's all.
Exactly. I believe it looks like a marketing thing. In many years ago, they named it nonlinear Schrödinger equation, and it's kind of sticky. So how are you going to solve this nonlinear Schrödinger? Well, we know that there's no analytical solution. We know that we cannot solve it with pen and paper. It's actually something we know. So you have two solutions. You have two ways of solving it. One, you need to do numerical simulation like we do, or you need to learn German to propose ansatz. Does anybody know ansatz? How to propose an ansatz to a formula?
Yes, a solution.
Yes. Ansatz in German means answer. You are getting an answer by looking to a nonlinear differential equation. You say that it should look like this. This is my answer, and you write some coefficients. And with mathematics and the systems coefficients, you try to squeeze. You try to limit all your coefficients in your answers. If you can limit all of them, your answer, your ansatz is complete, and it's a nice solution, okay? Rather than that, there's no way of solving. So you need to go with simulation. So simulation is simple. Let me teach you something called split-step Fourier. Split-step Fourier method is this. You can write this nonlinear Schrödinger equation like this. You can sum different terms as different operators. For instance, we call it dispersion operators, right? We call this nonlinearity operator, nonlinear operator. And our equation looks like this. Okay, can we solve it? Let's see. We can try. And this is the trick. We need to apply this formula, Baker-Hausdorff formula. It tells that if you have two non-commuting operators, like this exponential stuff, we can write as summation. Okay? And likewise, vice versa. And now we can write these equations answers like that. So we can split dispersion and nonlinearity for tiny steps and apply first dispersion or nonlinearity and apply the other one later. Okay, then we can solve the simulation. We can solve this nonlinear Schrödinger equation in the manual. So nobody likes the numerical derivatives. We need to get rid of them because we have derivatives here. I don't like it. So because it takes a lot of time in numerics, what you can do, Fourier transform tells me that derivative is actually nothing but multiplication and frequency. Okay? So I can take the dispersion operators and I can convert it to frequency grid. And when I do that, this derivative will be replaced with this coefficient. It's multiplication frequency, okay? There's no numerical derivative, which is nice. I just need to take the operation, I need to take this guy, take this Fourier transform, to appear the dispersion operator and frequency grid, and apply it in exponential term, and go back to our original domain, time domain, and inverse Fourier transform. So this is the actual algorithm. You have a complex envelope, take its Fourier transform, apply the dispersion, apply tiny h propagation, because h is here, right? Propagation distance. Take inverse Fourier transform, apply your nonlinearity with h, and repeat it until you reach the end of the wavelength. When you do that, it works. And if you have the second order, third order derivatives, or third order dimensions, when it happens, when you have multi-mode wavelengths, now you have to consider these guys, these ugly guys as well. So don't worry, it's actually simple. Like you did to time derivative, you need to create a special frequency grid, and you have to make the multiplication there, okay? And this is also linear equation. This is actually just multiplication, which is okay. The only big problem here, this is actually special temporal nonlinear multiplication, right? The only problem here is you need to take FFT of a three-dimensional array. For those working with numerical simulations, three-dimensional FFT is actually taking a lot of time, and it's not a good thing. So you need to either get your code prepared in GPU, like I did, or you can do this, you can decompose your electric field to different modes and consider single mode propagation for each mode, but they need to couple with each other, and they couple it nonlinearly. When they have an overlap, they can couple, and you can solve this guy as well, but the problem of the complexity of this algorithm is a bit funny. It works nice until you have 10 modes. After that, it's really slow. Okay? That's the reason we like to go with this guy. If you go here, you will get a code, and I will share it you wanna continue with the discussion? Okay. Give me a second. Efendim? Ha, tamam. If you go to GitHub, okay, if you go to here, you will have this guy, and here inside you will have two codes. One for single mode fibers, and another for multi-mode fibers. And the same thing, now I will run it here, in my computer. You can see it, right? Okay. There's my Jupyter Lab. Let's go to Jupyter Lab. Okay. Same thing, simple. Everybody knows Python, right? Everybody knows it? Most of us. Okay. So Python requires NumPy, matplotlib for images, for plotting. We have this function which we define according to the piece of code which I suggested a couple of minutes ago. What happens is you send the complex field, it takes its Fourier transform, okay? And then in the Fourier domain, we apply our dispersion. Inside this dispersion, we have the tiny dz as well. And then from there, we go back to time domain with inverse Fourier transform. And then later, we apply our nonlinear propagation with again same dz. In this code, I have a trick. I can stop here, right? I can do just, dz time, dz dispersion, dz nonlinearity. But if you study the error of the code, error of the algorithm, you will notice that it's a bit not good for tiny femtosecond pulses. That's the reason what we do is actually we create something else. We call it symmetrized step Fourier. How it works? You apply the dispersion for the half of your step, like I did here. You apply the nonlinearity of full step, then the remaining half of the dispersion. If you do that, numerical error will shrink and we will get nice results which will be same as the experiments. And for that, we take the second half of the dispersion here. We define some values like speed of light. This is the central wavelength frequency. We are the central wavelength we are propagating, and this is our light color. We define a time grid because this is a single mode simulation. We just need time and sporadus frequency. And this is our time, t. And based on that, based on the sampling rules, we define a frequency grid. And this is the wave frequency grid, this is the wavelength. We need to convert everything to angular frequency, and we need to center it around the central wavelength. This is the reason we are doing it, okay? Normalized angular frequency. Kerr effect of the silica, 2.7 for 1 micron. Beta 2 and beta 3, we calculated by taking the derivatives of the refractive index. We calculated the gamma, which you saw, the refractive index times the central frequency, central wavelength, divided by the speed of light, times the angle, the area of the refractive which you are propagating. Fiber length is around 10 centimeters. Our tiny steps are actually 1 millimeter. It's not that tiny, but it still works. And we define a dispersion grid in Fourier domain. Okay, this is the dispersion operator we defined in Fourier. This is our pulse. Pulse energy is not bad. 500 nanojoule. Our pulse duration is 500 femtosecond. This is a nice Gaussian. Okay, and we calculated this integral to see if we do it correct or not. And then we send our field to the function. It does the propagation, and after that, you will get input-output pulse shape and also input-output spectrum. Okay, let me run the code just for fun, and you can see how fast it is. And this is running in my computers, not bad computers. As you can see, it runs well. And if you're wondering, let's say this is the spectral changes, and I'm plotting in logarithmic scale to see it just for fun. Let's decrease the energy. Spectrum is less, and we can decrease one more time. The same one. less broad. Okay? This is simple single mode waveguide simulation. And you can do the same thing for multi-mode. For the sake of simplicity, I have two-dimensional code here, and I don't care the time, which means I'm dealing with continuous wave lasers. Lasers have no change in time, and I can ditch the time. And I have a multi-mode waveguide, and I'm studying what happens to the space. Okay? I have a filter to filter out the light which goes to cloud in my simulation. And same thing here, I define the spatial domain, Fourier domain for the space, and the operators. I have the reflected index profile of a piece of fiber, and I have the diffraction in space. And based on that, we define the light and let it propagate. This is my input, two-dimensional Gaussian, and does the same thing. And at the end of my simulation, my spatial distribution looks like this because I send a pump I send a laser light with 30 megawatt peak power, which is really, really high power, right? It will have nonlinear propagation. Just for fun, let's go to 3 and run the code. 5 more minutes. So here, small changes. Okay? Why it's not nonlinear? As you can see, you can get the code it's online right now. You can get it in GitHub. You can download it. You can play with it. It's yours as long as that's it. Yeah, there's no limitation there. Let me go back to my own slides, and then we can finish the course. Why we need nonlinear optics? Why I hold you to that? What was the reason? Well, reservoir computing, memory computing, more than 100 doesn't matter. They all have nonlinear activation functions. Although they look simple, like sigmoid, tangent, hyperbolic, whatever. When you have thousands of them in cascade, in parallel, accumulated behavior is actually complex. And if you don't have nonlinearities, a giant neural network is nothing but a single matrix multiplication. Okay? Because you can sum it and create a one single matrix. So you need nonlinearities to perform nonlinear information processing. And we need these in optics to do all optical computing. Okay? Otherwise it doesn't work. For instance, I showed the upper part yesterday as well. Neural networks perform this nonlinear propagation, this nonlinear matching of information. Can we do the same thing in piece of fiber? It's a simple question. Why? Because in piece of fiber, if you have a peak power around 30 kilowatt, right? Then propagation will be very complex and nonlinear. So if it is the case, can we use a piece of fiber to replace a neural network? What we need to do, we just need to shape the laser beam like our information, couple the piece of fiber, let's propagate according to this formula, right? And at the end of the fiber, it looks like this. For us, it has no meaning. But maybe if you use a single line of regression or classification, depending on the task we want, that is simple classifier. Okay? If you apply this simple classifier to the data set immediately, the accuracy will be low because it's a challenging task to do, right? But what will be the performance of the simple classifiers when we send the information which we get after optical processing? Okay? This is the simple question which I asked during my postdoc 3 years ago. Sorry, PhD. Optical setup, optical setup is simple. You have special light modulators. Everybody knows what's a special light modulator because a nice instructor already taught you yesterday, right? And then with special light modulator, you can encode information to laser light. You take a piece of nice lens, you take its Fourier transform, lens focus, it actually takes Fourier transform. and then it couples to the piece of fiber. Propagates according to the equation I teach you today, right? And at the end of the fiber, you have two lenses for your imaging. And you image what happens to the what the spatial temporal information looks like. And your camera is slow, unfortunately. It will take the summation in time, so you will get a beam profile actually at the end of the fiber because you already have a beam and input, right? And then, depending on your task, you can apply revelation or classification, and you can see what's the accuracy. Okay? It looks like this if you decompose to the modes. Okay? Complex field, modulated is actually phase modulation, Fourier transform, mode decomposition, with nonlinear propagation, and E is image to the camera. Camera measures under the square, additional nonlinear, but it doesn't affect too much. And you have the decision layers. Let's say I have a data set of different people speaking digits. It's an audio digit data set, thousands of audio files. And different people say 1, 9, 8, something. Okay? And you take this audio file, it looks like in the data processing part, it's nothing but a one-dimensional data. I don't like it because I have two-dimensional grid. We can generate a spectrogram, which is a simple trick, and use this data and send it through the fibers with different laser pulses. And then at the end of this file, we collect the optically processed information and ask the question, what are the digits? Almost 95% test accuracy. It's actually similar to the neural networks. Okay? You can change the question. Who was the speaker? In this data set, they had 6 different speakers, although they tried to make different accents. Okay? Now you don't need to do the experiment from scratch because the experiment is already completed regardless of last layers. You change the task, but the information is already processed. Right? You don't need to do the experiment, you just need to update the last layers. We updated again around 95%. Likewise, at that time there was something called COVID. Maybe you don't remember. And we had an ugly data set. It was actually a combination of 3 different hospitals from Brazil. And it had a really ugly data set with doctors handwriting, notes on the edges, different resolution because the X-ray machines are different in each hospital. And we asked a simple question. Does this guy have COVID or not? Okay? And we had not bad results. Again, if you use a giant neural network, it gives you the same results. Okay? And one thing, accuracy changes with laser power. Why? Nonlinearity. Strength of nonlinearity changes with laser power. Because of that, accuracy changes with laser power. So, nonlinear optics is actually the reason we have this good accuracies. Thank you. This is the reason we need nonlinearities.